Yeah, welcome and good afternoon, everybody. It's my great pleasure to have Edward Farhi here with us in Santa Monica. Actually, the main reason that Edward is here is to work with us and help us with our efforts in quantum computing. And while he was here, he actually graciously offered to give a talk. And this talk will actually not be about quantum computing, since some of you may recall a half a year ago when Edward was here, he already addressed his latest work in this topic. And so we thought it may be much more fun to talk about the recently started up.
Conference number followed by the pound key.
Okay.
Or press star to create a new conference.
Okay, sorry, there were some audio issues. So yeah, we thought it's much more fun to talk about the Large Hadron Collider. And this is what the talk of Edward will be about, and we'll leave it as such.
Okay, well, thank you. Can everyone hear me okay? Okay, well, I'm sorry?
They can't see you. No, I should look at it. Okay.
Am I okay? Am I all right? So this is going to be a talk about the Large Hadron Collider, which is the giant accelerator that everyone knows is turning on in Geneva, Switzerland. And although I work on quantum computing, I got my start in particle physics, and I do know a little bit about particle physics. And I worked at CERN for a year before the Large Hadron Collider was built. I worked there, and so I feel I have a pretty good idea of what the issues are that are going to be addressed by the Large Hadron Collider. I would like to say another thing. I am a theorist, so I really don't know that much about how it works. To me, it's just this amazing machine. It's the most complicated thing ever built. And I decided not to stand here and show you pictures of it, because I can't really explain the pictures other than to say this is an amazing piece of apparatus, and you can just go on the web and look for pictures of the LHC yourself. So my goal is more to try to explain to you a little bit why it is that physicists are excited by the LHC. And I understand that most of you probably have backgrounds in computer science and engineering. I don't know how much physics you know. So please feel free to ask me questions, because I want you to understand. And I will alter my talk if I discover that I'm addressing issues that are opaque to you. So, and the only thing is, if you ask me something, I'll try to repeat the question so people remotely can hear. Okay? So the Large Hadron Collider, it's the most powerful particle accelerator ever built, and it's going to smash together protons on protons, and the protons are moving. The energy of the protons is 7 TeV. So let's just set the scale here. I'm going to use very rough units, okay? And E equals mc squared. So if we set the speed of light to 1, we can measure mass and energy in the same units. So the standard unit I would like to use, just so we can wrap our head about it, is a GeV. A GeV is the energy a particle with the electron's charge gains if it moves across a GeV is 10 to the 9 volts. So it's how much energy a particle picks up. And in a GeV units, the mass of the proton is about 0.94 GeV. So that sets the scale. Okay? So the mass of the proton is about a GeV. And the LHC has energies. The energy in a beam at the LHC is a 7 TeV, and that's like 7,000 GeV. So for those of you who know a little bit about relativity, that means that the gamma factor, in other words, the energy divided by the mass of the particle, of the proton, is, let's say, about 7,000. So that means that, for example, the clock, if the proton is carrying a clock with it, it is, in its rest frame, that clock is going about 7,000 times slower than the clock on the, in the lab frame. And for example, it also means that the proton sees the accelerator as contracted by a factor of 7,000. So instead of it seeing 20 kilometer, you can do the arithmetic, I don't know, so maybe it's this big or something, the accelerator, in the rest frame of the proton. And of course, these relativistic effects have to be taken into account or the thing would not work. So these things are being smashed together. And also, another thing you should know is that this is proton on proton. So there are two counter-circulating beams, and the particles are then brought together in collision. And the lab frame is the center of mass frame, because you have one beam going this way and one beam going that way. So the lab frame is the center of mass frame. And that means that all the energy that comes in the collision can go into making stuff. And you don't have to take energy to set something moving. If you have a particle at rest and you hit it and you make something, you still have to send it that way. But here, in the center of mass frame, you collide the two particles, and if you make something, you can make it at rest, which means all the energy in the beams can go into the production of new particles. That's why they built colliders as opposed to fixed target machines, to take advantage of that center of mass energy effect. So this thing is going to be up at 7 TeV, and that's about a factor of 10 higher than Fermilab, let's say, which was working at about a tenth of that. And this thing will also have much higher luminosity. The luminosity is a measure of how many interactions there are going to be per second. And maybe I should just, even though I'm not an expert on this, you should know that the data rates coming out of the LHC are so enormous that it would be absolutely impossible to write to tape all of the collisions that go at the LHC, because the number of collisions per second and the amount of information that the giant detectors will gather for each collision is so high that it would be impossible to record all the events. And what that means is, again, I really shouldn't talk about this because I'm not that much of an expert, I'm a theorist, but that really means that when the experimentalists decide, they have to make a decision, should we write the event to tape? I call it tape, I'm not sure it really is tape, but should we record the event? They have to look at some characteristic of the event and then make a decision, yes, we're going to keep it. And of course, that's called the trigger. And so obviously, when you're trying to design your data analysis, the trigger is crucial, because if you might trigger on something which is not the characteristic of the thing you're hoping to find. So there are a lot of really great subtle issues in data analysis at the LHC. I believe the LHC will be producing, more data than was ever produced by, all the phone calls in the world or something. There are all these analogies to how much data is going to be coming out. But the data rate is phenomenal from the LHC, and it's the job of the experimentalists to extract from this incredibly complicated data signal. And one of the real challenges there in looking for signals at the LHC is, since there is so much data and it is so complicated, it's very hard to look for things unless you know what they are. Because if I gave you an incredible amount of data and I said, look for something anomalous, well, that's a lot more complicated than if I said, look for a particular particle with this mass decaying in this channel. So knowing what to look for helps. And therefore, the prejudice of theorists about what will be seen at the LHC is very, very important, because the theoretical prejudices of what might be discovered affect the way the experimentalists look at the data. And of course, our hope is that the experimentalists will not listen to us, that the experimentalists will not pay that much attention to the theorists, will look for things that they have decided are really the good things to look for and find one of them. That would be the ultimate thing. Now, what is it that we want at the LHC? Well, in order to talk about what we want at the LHC, we need to talk about where we are in particle physics. So let's go back and talk about what do we know in particle physics now? What are we really sure of? And it's actually remarkable how much we know in particle physics. Let me tell you what we do know. Well, first of all, I'm not going to talk about gravity unless you force me into a discussion of string theory or something. So let's put aside gravity. The reason I'm putting aside gravity is basically, as you all know, gravity is an incredibly weak force at the level of particle physics. The gravitational attraction between two protons is minuscule and can be completely ignored in everything that goes on at the LHC. Don't ask me yet about making black holes or something. Let's forget that, okay? So let's just talk. I'm going to stick with the standard line. I'm going to give you the party line on particle physics before we go to the exotic. You can't go to the exotic till you first do the party line. So on the party line, gravity is incredibly weak, and we can ignore it. And then, there are three forces of nature then at work at the LHC. There's the strong interaction, which holds the proton together, the quarks inside the proton, and which is responsible for most of the stuff that's going to be seen at the LHC. There's the weak interaction, which has to do with the decay of particles, and there's the electromagnetic interaction. And we can talk more about these in a few minutes. Now, so there are basically three forces in nature at work at the LHC: the strong interactions, the weak interaction, and the electromagnetic interaction. And as far as we know, those are the only three forces of nature. We could speculate about other forces, a fifth force. Oh, because when I say a fifth force, that's because we add in gravity. So there are three particle physics, and then there's gravity. So when you talk about the fifth force, that would be beyond that. But for our purposes, there are three forces of nature. And what we do have, quite remarkably, so we have forces, but then we need to have a list of particles that interact. And there is a short list of elementary particles which we have discovered to date, which are described by, which interact through these forces. Okay? And I could list those particles for you. The list is not very long. Let's just start with the fermions. Those are the spin-half particles. So for the fermions, there's the electron, the muon, and the tau. The electron we all know and love. We're made of electrons. The muon is a cousin of the electron. It's just like the electron, but much heavier. The tau is a cousin. It's just like the mu and the electron, but it's much heavier. Then we have the three neutrinos. And then we have the quarks. We have the up-type quarks. I call them up-type because they have a charge 2/3, up, charm, and top. And then we have the down-type quarks, down, strange, and bottom. So we have a list of 12 fermions, all of which have been seen in some form or another, either indirectly or directly. They all have mass. And what's very interesting about these particles is that they come in groups. So this particle, and this particle have the same charge and the same quantum numbers. This particle, and this particle have the same charge, 2/3, and they're both triplets under the color force, if that means anything to you. This is down, strange, and bottom. They're all charged minus 1/3. And because these are quantum mechanical particles with the same quantum numbers, they can actually, sometimes you're forced quantum mechanically to consider linear combinations of them in certain processes. And that's actually, I could maybe talk more about that. That's what the Nobel Prize was awarded for last week, was figuring out something about the linear combinations of these particles which interact in the weak interactions. Maybe I'll tell you about that later, because it's very topical. I could tell you why Kobayashi and Moscow won the Nobel Prize. I cannot tell you why Kabibo wasn't included. That's a political thing. I don't know. So the Italians are all upset about Kabibo not getting the prize, but the Japanese are happy because of Kobayashi and Moscow. Now, these particles, this list, is just handed to us. We don't really know where it comes from. We just have this list. And then we have a description of the forces between these particles, and that is described quantum mechanically, if this means anything to you, in terms of a Hamiltonian. The Hamiltonian is the thing that determines the dynamics quantum mechanically. Once you know the Hamiltonian of a quantum system, you know everything about the quantum system, assuming, in principle, you know everything. And that's because all quantum systems obey the equation I d by dt on psi, the wave function, is h psi. So let me just tell you what this equation means. It means that if the psi is a vector and h is the Hamiltonian, and this is a time evolution equation, and it tells you that if you know the state of your quantum system at one time, its future is determined by solving that differential equation. So the Hamiltonian governs the dynamics of the system, just like the force in Newtonian mechanics determines the dynamics. If you write F equals ma, if you know the force, you know the future. Quantum mechanically, if you know the Hamiltonian, you know your state vector, you know the future. So the Hamiltonian contains all the information about the interactions of these particles, and we have written, I shouldn't say we, other people have, peoplekind, have written down the Hamiltonian of the strong, the weak, and the electromagnetic interactions. Those Hamiltonians were written down, and they were really completed in the late 70s and maybe the early 80s. And the amazing thing about it is that if you take the Hamiltonian of the strong, the weak, and the electromagnetic interactions, and you take these particles as input, and then you ask a question like, what is the probability that at a certain detector, at a certain accelerator, when I collide together two particles, two other particles will come out at a certain angle? You make the prediction, you compare with the experiment, dead on. You calculate a property of the muon. You know, the muon, for example, this particle over here, it's a spin-a-half particle, which means it carries angular momentum, but it also has a magnetic moment. Because it's a charged particle, it has a magnetic moment. And you can ask, what is the ratio of its magnetic moment to its spin angular momentum? And you can calculate that in the standard model, and you calculate it to 10 decimal accuracy. And the prediction of the theory agrees with experiment to 10 decimal accuracy. So when you can make 10 decimal predictions, you feel like you have confidence that you have some understanding of your theory. And it's more than that. It's that the standard model of the strong, the weak, and the electromagnetic interactions, there has not been a single prediction of the standard model that has been that contradicts a single experiment. So this is kind of amazing, you know? We live in a time when we know the forces between quarks, and we have a mathematical framework for making calculations. It's called relativistic quantum field theory. I teach that class. So we have a mathematical framework for making predictions in this theory, and it allows us to make predictions about properties of particles, and it also allows us to make predictions about what will happen in collider experiments or in other kinds of experiments. And again, I cannot emphasize to you enough, every prediction of the theory, every calculation that has been carried out when compared with experiment is in agreement. And that's pretty remarkable. Now, that doesn't mean that there is not lack of understanding or unhappiness in the particle physics community. Where does that unhappiness come from? It comes from the fact that the theory has a lot of arbitrariness in it. For example, let me give you an example of the arbitrariness in it that we feel like shouldn't be there. We just have an intuition that this arbitrariness shouldn't be there. For example, we input the masses of all these particles as inputs. Okay? We input them into the theory, and then we make measurements, and then we just adjust the input to agree with the measurement. So for example, there's a parameter in the standard model, the mass of the electron. And then, well, you know, you go out and you measure it, and you discover the mass of the electron is 0.511 million electron volts, because I'm measuring mass in energy units. It's 0.511 million electron volts. That's the value you put in. End of story. Now, once you have that value, you might use that as input to making another prediction about some other property, but that's an input. And the masses of all the particles are inputs. But there are some very strange aspects to it. For example, if you look at these, let's just look at these three quarks, just as an example, okay? These three quarks. Well, the top quark, which is the heaviest quark, its mass, the mass of the top, is about 170 GeV. Okay? Huge. Remember, the proton is 1 GeV. So the single quark has the mass of a giant atom. Okay, but it's an elementary particle just like the up quark, but it's a single quark and it has a mass of 170 GeV. That's like somewhere high up in the periodic table. Something that has, it's like something that has 170 protons and neutrons. Okay, that's how much it weighs. The mass of the charm quark is 1.5 GeV, and the mass of the up quark is about 0.005 GeV. So here we have three particles, identical in all respects, but have incredibly disparate masses, which we take as input. That seems very unsatisfactory. And it's very atypical. Like, for example, just think about, think about something like chemistry, right? Suppose I told you, well, let's look at the periodic table before you knew how to order it. And you had all these elements, and it all looked very scattered and very complicated. But then once you realize, for example, that the nuclei of atoms are made of protons and neutrons, you get very quickly a good rough estimate of the mass of the atom. Right? The mass of the atom is roughly, the number of nucleons times the mass of a nucleon. And that works very, very well. I mean, you just go right up the periodic table up to little corrections from binding energy and throw in a few electrons. I mean, that's the basic picture, right? The mass of an atom is the sum of the masses of the protons and neutrons in the nucleus. That's it. Very simple. But in that kind of picture, it's very hard to imagine a mass ratio like this. Huge mass ratios in the Standard Model. And this is completely not understood. And this weirdness of these mass ratios persists everywhere. Like the electron weighs 500,000 electron volts. This is 1 billion electron volts. And this lepton weighs over a GeV. So this huge disparity in mass is a tremendous mystery in the Standard Model. There's another problem in the Standard Model, which is this. Basically, what are we made of? Well, we're made of up quarks and down quarks, because protons and neutrons are made of up quarks and down quarks. And then we're made of electrons. Now, why are we made of electrons and not muons or taus? I just told you they're very, very similar. Well, the reason is very simple and not that deep in a way, and that is heavy particles decay into lighter particles. So, for example, the muon can decay into an electron plus 2 neutrinos. So if I have a muon and I put it on the table, it'll spontaneously decay into an electron. Now, the electron is the lightest charged particle. Now, if you believe that particles decay only into lighter objects, and you believe in the conservation of charge, then the lightest charged particle is stable because it's got nobody to decay into, right? You think about any decay chain, it ends at the lightest charged particle because the lightest charged particle can only decay to another charged particle because conservation of charge, and there's nobody lighter. So the distinction between the electron and the muon is that the electron is stable by accident of it being at the bottom of the list. And of course, that makes it a very good thing to make us out of, because it's better to make people and stuff out of stable things. But it really has nothing to do with its fundamentalness from the point of view of particle physics. So to a particle physicist, all these particles are equally fundamental and equally interesting. It's just that we happen to be made out of electrons. And we also happen to be made out of protons and neutrons. And of course, the proton is the lightest particle that carries baryon number, so it can't decay. Let's not go into granularification or something, but roughly speaking, the proton is stable. So, it's a convenient thing to make things of because it's stable. But it's not a fundamental thing, it's just an accident. So one of the things that we really don't understand is, why is this pattern repeated? And there's a very famous quote, from I.I. Rabi, because after the muon came to be, he said, "Who ordered that?" Like at the Chinese restaurant, where'd that dish come from? So he couldn't understand where the muon came from, and that has just continued. We now have what we call 3 generations, 3 sets of particles, absolutely no understanding for why it's 3, but we really don't think it's 4. Certainly not with very light neutrinos, because there's a certain decay of the Z boson, which you can look at. I could explain this if you force me. But if you look at the decay of the Z boson, you would see, you can count the number of massless neutrinos, or almost massless neutrinos, and the number is 3. And there, you can also infer that from certain early universe data. So it looks like this is the list, as long as we assume that the neutrino, if there are more of these out there, that the neutrinos associated with the next generation is light, then this is the list. So physicists, they don't like this. They don't like the fact that there is a group of particles whose properties are seemingly very, very arbitrary. And in physics, the goal is very often to try to remove arbitrariness, to try to get some larger picture, just like we have in chemistry. Right? Chemistry is not mysterious in a certain way. It's very difficult to understand maybe detailed chemical reactions or properties of complicated atoms. But if you ask me about the periodic table, it's all determined once I tell you I have protons, neutrons, the strong force to keep the nucleus together, the electromagnetic force to keep the electrons buzzing about, and quantum mechanics. Then the entire periodic table is determined. Right? So there's no mystery in chemistry at a fundamental level. It's all determined by underlying physics. Yet we have no understanding of this. Now, of course, I didn't tell you about all the particles. There are other particles in nature. There are the force carriers, which are associated with this. Let me just talk about the weak interactions for a minute. In the weak interaction sector, there are two particles called the W plus minus. I call that one particle because the plus and the minus are antiparticles, and the Z boson. And both of these particles have been found. This weighs about 80 GeV. And this weighs about 90 GeV. They've both been made. They decay. All their decays are consistent with the standard model. And there they are. Now, but there's another particle. There's one particle in the standard model, one, which is part of the standard model but has not yet been found. And that's called the Higgs boson. The Higgs boson. And the Higgs boson is an integral part of the electro-weak, or the weak interaction part of the theory. It's a key ingredient to the theory. But it has not yet been seen. And not only that, its mass is also a free parameter, something which we do not yet know based on first principles. So it's not known, it is not specified by the theory. However, I told you that you can do detailed calculations in the standard model of processes. And those detailed calculations of processes rely on our understanding of the existing particles. So what you do is you put the Higgs particle into the calculation. Even though we're not talking about a thing in which an actual Higgs particle is made, I'm going to use the Higgs particle as an intermediate step in part of a more complex calculation. And then what you discover is that there are certain observables of things which have been seen which depend on the mass of the Higgs. Okay? So from the existing data, you can go and say, what is the most likely value of the mass of the Higgs in order to fit the existing data, since some of the experiments, some of that data actually is sensitive to the mass of the Higgs. Does that make sense? And it turns out if you do that, you pick the mass of the Higgs to be about 90 GeV. Okay, 90 GeV. Well, it turns out that if the Higgs weighed less than 115 GeV, it already would have been made at Fermilab. Because what we have now, how can I say it? What we have now, we have limits on the mass of the Higgs. In other words, what we can say now is, if the Higgs weighed less than 115 GeV, then we already would have made it at Fermilab. Okay? So the most likely value for the Higgs mass based on pre-existing data is lower than the experimental bound from Fermilab. So what you can then do is something else. You could kind of make a confidence curve for the mass of the Higgs. And you could say, let's say how likely it is based on the data. So I just told you the most likely value is like 70. So I'm going to make some likelihood curve. I'm just drawing some likelihood curve. The most likely value is 70 based on the pre-existing data. However, it's excluded on this side by experiment. So it means that the mass of the Higgs is to the right of 115 with some falling curve out from 115. So if you had to bet on what the mass of the Higgs is, you would probably say, it's 120, 130, 150, because it's getting less likely based on the pre-existing data. And that means that the LHC will find it, because the LHC has the reach, it has the energy capability to produce the Higgs boson. In fact, what you should really say to me is, look, the Higgs boson, if it only weighs 115 GeV, why do I need 7 TeV to make it? Because E equals mc squared. So you'd think that if I collide together two particles, I could convert all that energy simply into the mass of an object. Because I'm colliding together particles, and I'm making something. But the reason is because one of the things that goes on with the LHC is it's a proton-proton collider. And a proton is a little dirty bag of 3 quarks and a bunch of gluons. And what actually collides at the LHC are the quarks inside the protons. And the quarks inside the protons are not carrying 7 TeV. They're carrying a smaller fraction of the energy and momentum because they're just constituents of the proton. So what's actually happening at the LHC is you're smashing together 2 little dirty bags of quarks. And the quarks collide, but they don't each carry 7 TeV. They carry a much smaller fraction. And that's why the LHC could never make a 14 TeV Higgs boson, even though you have 14 TeV in the center of mass, because you're never going to find 2 quarks carrying all the momentum of each proton. So that's why the reach of this is a little bit lower than you might have thought, going all the way to 7 TeV. So the betting money is that the LHC will discover the Higgs boson, because the Higgs boson is a key ingredient in the Standard Model, which to date has been 100% successful in all of its predictions. Okay? I should say something else about the Standard Model, which is, I think, worth understanding. People talk about all kinds of models where they have extra dimensions and supersymmetry and all kinds of variants of the Standard Model. And basically what happens is, as soon as you muck with the Standard Model, as soon as you change it a little bit, you make a prediction that's inconsistent with experiment. The only way, really, that these models manage to be consistent with experiment is to have an enormous number of free parameters. So the way that the theories that are supposed to go beyond the Standard Model, if you actually look at them and say, how do they manage to be consistent with the current existent? It's because they have so many free parameters that they can adjust, they can match the Standard Model. So if you actually ask yourself, I try to be a little bit objective and say, what is the alternative to the Standard Model that actually is let's say, either makes a prediction, a postdiction. A postdiction would mean explain something we couldn't already explain, or a very clear, let's say a postdiction, so explain something that we couldn't already explain, and that is in some sense minimal and not excessively complicated. The answer is nothing. So one of the amazing things about the Standard Model is not only is it enormously successful, very frustrating because it has all these free parameters, but it has no competitors. It has no competitors. And by a competitor, I mean an alternate theory which actually explains something which is not in contradiction with experiment. It doesn't have competitors. And that makes it very, very hard to understand also why it's so good. So I would say the odds-on bet is that we'll find the Higgs boson. I've set up a betting pool at my work for the mass of the Higgs, and we've been taking bets. I would bet it's going to be 150 GeV or something, and they'll find it, and it'll probably decay into, according to, and also in the standard model, given the Hamiltonian of the standard model, we know it's decay channels. We know it's favored decay channels, and the most likely scenario that will come out of the LHC is that the Higgs will be discovered and it will decay in the way predicted by the standard model. And in a way, if that's all that's found, it will be a big disappointment. That's in a way the worst possible outcome. The worst possible outcome for the LHC is the Higgs boson is created, it decays according to the rules of the standard model, and nothing else is found. I would say that would be a disaster for particle physics, because it just means that we built this enormous machine and all we did is confirm what we already knew. And since we can't predict the mass of the Higgs, if it turns out to weigh, 100, just like the numerical value of the mass of the top, it doesn't inform anything. If the mass of the top were 173 GeV, nobody's theories would change. It's just an input. Just like if the mass of the electron were twice what it is, nothing would change. You would just have a mass of the electron that would be 1 MeV instead of 0.5 MeV. That's it. I mean, maybe it would have implications for chemistry or something. Maybe it would have implications for devices, but it would have no implications for fundamental physics. And so I would say that at this point, if we find an intermediate mass Higgs, a low mass Higgs, then it's very disappointing in some deep way for particle physics. The alternative would be to find a very high mass Higgs. If we find a very high mass Higgs, then it's hard to account for the existing data. That would be more interesting. Another possibility is we don't find a Higgs at all. Well, that would, of course, mean only that we place a limit, that we say if the Higgs weighed, let's say, less than a TeV, with high probability it would have been produced after 5 years of running of the LHC. That you can never exclude it entirely. You can only say, with a high probability, had it been in this mass range, we would have made it. So if that would be very interesting to the particle physics community, the non-existence of a Higgs, that would be great. In a certain way. No Higgs, I'd love that. That would be great. Because then you'd really be in trouble. Now, obviously, the thing we want at the LHC is something we didn't think of, right? That's obviously what we want. That's the hope for the LHC. The hope for the LHC is that some particle will be made that no one ever thought of, or some cross-section. A cross-section is a scattering probability at given angles. It is going to go down when we thought it should go up. That's what would be the best thing. Some weird phenomenon which is absolutely unpredicted. And I really hope that that is what is found. And I would say most of my colleagues hope that that's what's found. Now, again, the scary part is, as I told you in the beginning, the LHC has so much data that it's very hard to know how you would see something anomalous unless you knew what you were looking for. That's one of the difficulties of the experimental program at the LHC because it's so complicated. You don't know, if you don't know what feature to select, how do you say it's an odd feature when you have data sets which are unimaginably big? And so that is a huge concern at the LHC for people like me. I mean, how do we really gain confidence that the experimentalists are not going to overlook something simply because they didn't look for it? And that's terribly scary. Well, wait, maybe I should, are there any, I've been ranting. So anybody have any questions about, up till now? Because I'm happy, yeah.
So you said that the number of generations, we know there's no more leptons because we would have noticed if there were any more leptons.
Right.
But how do we know there's no more quarks?
Well, let me tell you why. One thing we do know, there is a constraint in the standard model. Let me just see. Hold on. How can am I sure of that? The theory, as we write it down now, if it doesn't make sense. Actually, it's not mathematically consistent unless you have all four particles at once. There are certain the existing standard model has certain constraints on its particle content, which are satisfied by these. And if you added simply a lepton doublet, meaning a new, let's say, neutrino and a new corresponding lepton, there would be something wrong with the standard model. So the general thought is that if you add this, you have to add this to not encounter that problem. Now there could be other problems, but the standard law is we call this a generation. A whole generation has to be added, or else you would have to have some other explanation for a little math problem which I didn't tell you about. So there is some hint that particles come in generations. And actually what happens is, I could tell you how they know how many neutrinos there are. You see, the Z boson decays into neutrinos. It decays into many, many things, but in particular it decays into BB bar, that's a anti-bottom quark, and it decays into neutrino, antineutrino of all three types. Now, when a particle decays, that induces uncertainty in its lifetime. I mean, there's an uncertainty in the lifetime of a particle, which is, how long does a particle stay on the table? Well, that's its lifetime, and the more channels it has to decay into, the shorter its lifetime, because the more things you can decay into, the shorter your lifetime. Now, when you produce a particle energetically, the uncertainty in its lifetime reflects itself in the uncertainty in the energy at which you can produce the particle. So, for example, when you produce a particle like the Z boson, the Z boson weighs, 90 GeV. But if I plot the production cross-section versus energy of the Z boson, it's actually peaked at 90 GeV. And because there's a little spread, and the reason there's a little spread in energy is it's come from the time energy uncertainty principle, if that means anything to you. So there's a little spread in the energy at which you could produce these things, and that arises because the thing has a non-zero lifetime. And if the lifetime were narrower, this would go the other way. And for a very long-lived particle, this is very narrow. So this production cross-section is a measure of the lifetime of the particle. So even though the Z boson can decay into neutrinos, which are not detected, by studying the production cross-section, you measure its width, what we call its lifetime width. And by measuring its lifetime, we count the number of neutrinos. It's kind of amazing. Even though you don't see them, we know. So now we know there are 3. If you fit the number of neutrinos from that data, you get 3. I think 3.1. Go ahead. Oh, because, yes, so the question is this. When what he's heard is that the mass of the Higgs boson is responsible for giving mass to all the elementary particles. So what he thinks is that if we find the mass of the Higgs, that somehow or another we get the pattern of masses. That's actually not true. I mean, what happens is that the Higgs, it is true that there is a coupling of the Higgs boson to each particle, which gives it its mass. I could explain that in more detail. But each particle has an arbitrary coupling. So there is many, in other words, but you could think about why what you're saying can't quite be right, because if 12 parameters could be predicted from 1, I could have constrained the data, even though I didn't know the mass of the Higgs. Right, I could have had 11 relations, and I don't. So the mass of the Higgs is a input parameter, which really, if it just turns out to be 150 GeV or something, will be very, very frustrating to theorists. People like to say that the LHC is going to discover the origin of mass. They say that. But if you already look at the standard model, the way mass is generated is by a coupling of the Higgs boson to the fermions. And the actual discovery of the Higgs is not going to change my understanding. So that's one of the scary things about the LHC. I mean, I already understand the standard model. And if they find the Higgs, I'll just say, okay, I always knew it was there. Nothing will change for a lot of theorists. And that's very, very scary. The only thing that's going to change things is if none of the above is found. But the discovery of a single, simple Higgs boson will change nothing about the way I understand the standard model. For example, I'm just using myself as an example, because I already assume it exists. And I don't have any handle on the mass parameter. And since I have no idea what the mass should be, discovering the number is not going to change anything. It's a scary prospect, I think. And I think that sometimes people oversell a little bit how much will be learned by the discovery of the Higgs. I think if we discover the Higgs and it decays according to the standard model, we'll have learned nothing other than our preconceived ideas were correct, which is reassuring, but it doesn't tell you how to take the next step. Because we would already anticipate the next step. Go ahead. How can we know we haven't found the Higgs boson? I'm not really sure what you mean by that. I mean, the Higgs boson is a particle which has definite decay properties, and in certain experiments, they collide together particles. The Higgs boson is very short-lived, and they collide together particles, and they say that if a Higgs boson had this mass, then in our detector, we would see these particles coming out with this fraction of the time at these angles, and they don't see it. Because the existence of the particle leads to very definite predictions about how things would work. And so when we say we haven't, the Higgs doesn't exist, we haven't seen it, we mean we take the existing theory, we say, given our knowledge of the theory, given a particular accelerator experiment like Fermilab, what is the probability that a collision would give rise to the Higgs? We multiply that probability by the number of collisions we have, and we say that if the Higgs existed, we would have seen it. Go ahead.
So it sounds like since you're placing your bet on the existence of the Higgs and maybe like a relatively low mass Higgs,
Mm-hmm.
then if the experiments don't, if the experiments reveal exactly that, then progress for particle physics, from your standpoint, it seems like it would have to depend on either like some kind of mathematical breakthrough or some kind of philosophical breakthrough, right? Like either a change in our ability to analyze these mass patterns,
Right.
or alternatively like some insight into like measurement or time.
Well, whatever, yeah.
Which of those two do you think?
Oh, I don't know. The question was, I'm supposed to repeat the question for the remote viewers. He says, well, if the Higgs is found and everything is according to what we know, how are we going to make progress in particle physics? Well, the honest answer to that is that has frustrated me so much that I have developed a second life doing quantum computing. And that's really one of the main reasons I have been working on quantum computing. It's because I have found it so difficult, personally, I'm telling you my personal story, to make progress in particle physics that I have developed a sideline. And if something really, really bizarre happens in particle physics, my interest in quantum computing will go down. But that's I can't really answer a question like that other than by telling you what I do. I don't have an answer beyond how I organize my life about what I think is the answer, and I think I don't know enough to do something else. Yeah.
Question for both of you.
Oh, sure.
So, why do we know why the weak forces has only one-handedness, and what constraints can we place on the existence of another cohort of particles which has the other handedness, but is otherwise the same as?
Yeah. Well, the question is,
love?
I guess everyone could hear that because it was broadcast. So the answer is, he's asking me, why does nature prefer one-handedness? Which is really the question of why is parity violated in the world? Why does the standard model violate parity? Parity is the symmetry that says if you look at the world and then you look at it in the mirror, that any reaction you see in the world, in the mirror world, you should be able to reproduce in the lab. And of course, that's not the case. And the reason for that is because neutrinos are left-handed. And left-handed means that their spin angular momentum points opposite to the direction of motion. Assuming they're massless, which they're not. But anyway, if they're moving this way, they're left-handed means that their spin goes the opposite way. Now, if you look at that in the mirror, when you reverse momentum, you don't reverse spin actually in a mirror. So in a mirror, a neutrino would be right-handed, and we don't see right-handed neutrinos. And that is a fundamental ingredient of the standard model, that parity is maximally violated. I would say there's absolutely no understanding of it, and it's just the way it is. And in fact, I would say that if you're as an old dog like me, you don't even ask that question anymore. I mean, I just more say to myself, well, why should parity be a good symmetry? It just isn't. I mean, it's just not a symmetry of nature. I mean, so you thought it was, but it isn't. And the same is true of charge conjugation and time reversal, that although you would think that these should be symmetries of nature, they're not. But, you know, I can't really explain why they're not, but they're not. And I think it's better at a certain point to stop saying, why are they not symmetries of nature, and just say, well, that's the way it is. I don't know. Why should parity be a good symmetry? It isn't. I guess we, okay, yeah, go ahead. Well, maybe I should talk about the Nobel Prize. Do you want me to explain to you what the Nobel Prize was for this year? So the Nobel Prize this year was, well, there were two aspects to it. One of it had to do with what's called spontaneous symmetry breaking, and one of it had to do with neutrino masses, basically, mixing. Oh, no, not neutrinos, I misspoke. I misspoke, I'm sorry, with quark mixing. Well, remember I told you that these quarks are the same in all ways, up, charm, and top. And these quarks, down, strange, and bottom, they're the same in all ways. So that means that actually, quantum mechanically, you can be forced to consider superpositions. And when I talk about the up quark, usually we mean the quark whose charge is 2/3, which has a certain mass. When we talk about the down quark, it's a certain charge of -1/3 with a certain mass. But in the weak interactions, there are actually couplings between the up quark and the down quark. But now you have to say, is it the down quark, or is it some linear combination of these three? Okay? Because that's naturally what arises. The thing that the up quark couples to is something I call down. But what does down mean? Well, down could mean any of the down quarks, and what you have to do is take them in linear combination. Now, the history of it is this. It was known, in the old days, we didn't know about these quarks, top and bottom. And the very beginning, we really only knew about up, down, and strange. And also, when I say quarks, I'm putting a modern language on something which at the time was not so resolved as quarks. So it's a revisionist history. I'm using the language of quarks, even though they didn't use it at the time, because it's easier to explain it. And a guy named Cabibbo said that what the up quark mixes with is a linear combination down cosine theta plus s sine theta. And this linear combination is what is really the up quark couples to in the weak interaction, this linear combination. And this angle was called the Cabibbo angle. It always has been. Well, Kobayashi and Miskawa, before the existence of the top and bottom quarks, said the following thing. They said, imagine a world in which we had 6 quarks. Imagine a world in which we had 6 quarks. Then these 3 would mix. And there would be a linear combination of down, strange, and bottom that would appear here. And what linear combination you get, it was just determined by matrix algebra with certain free parameters. And they showed, though, that if you did the little matrix algebra, the linear combination of these quarks is expressed in terms of a unitary matrix. Quantum mechanics, a lot of the time you get unitary matrices. But there was a way to reduce that unitary matrix by making phase rotations. So it ended up, the linear combination had 4 parameters. There was a 4-parameter linear combination. And one of those parameters, though, they realized would give rise to the violation of time reversal, or CP violation, which had already been observed in the world, because Fitch and Cronin had already shown that time reversal, or CP violation, which is actually the same thing, is not a good symmetry of the world. So what they realized is that if they extended the quark model to include another quark, they could account for CP violation. And that's a good prediction. I mean, if you can extend the theory, account for CP violation, and then those quarks are discovered, well, then you really had a good insight in advance. And what's amazing is that those 4 parameters, which make up something called the CKM matrix, the Kabibbo-Kobayashi-Muskawa matrix, those 4 parameters are determined by at least 50 experiments. So you have 4 parameters and at least 50 data points, and they're consistent. In other words, the 4 numbers in the Kobayashi-Muskawa predict 50 different experiments consistently. So it's a beautiful theory of quark mixing, which in advance predicted CP violation in the Standard Model and has correctly parameterized the weak interaction mixings since its invention. So it was a very deserving prize, in my opinion. I mean, why they left out Kabibbo, I don't know. Yes? Sure.
So, as far as I understand, the theories predicting that was about 70
About what?
About 70 GeV.
Well, the most favored value based on current data, except for the fact that it's excluded.
Okay, so yeah, actually the thing I was wondering about is, okay, we haven't found it yet, but the detector that should have found it, so the mass may actually be higher.
A bit bigger than 115, right.
Yes, but how come then that we have found with W and C boson, which are actually heavier?
No, they're not, because they weigh 80 and 90 GeV. Why did we find them? Oh, just because they're produced in different channels. Oh, you're saying, how can we find the 90 GeV? We already produced the top quark, which weighs 170 GeV. It's because it sticks out more. It's because the signature of the top is much more striking than the signature of the Higgs. And the production cross-section is much higher. So it's just a question of signal. It's a question of signal. It's not a question necessarily of the mass. We have the energy to produce the Higgs, but you have to have the signal. You have to multiply the probability of making it by the luminosity times the probability of detection times the number of years you run your detector. And the Higgs, the top quark could be made and the other one couldn't. It's a question of the details of the production cross-sections. One thing I haven't said though, well, I mean, I've only had an hour and I'm going over, but I have not, at all dwelt upon alternative theories or weirdness. I've been giving you kind of a very orthodox and down-to-earth picture of what the LHC is. I'm just staying very grounded here. We could press me to get more, far out, but I don't want to do that right away because I think it's important to understand the framework in which the far-out theories might be, what they're competing with. I think it's important to understand what the far-out theories are competing with. There was a question, yeah. You didn't ask.
When the other particles were discovered, how did their masses compare with previous predictions?
There were no predictions for these particles. Wait a second. The W plus, minus, and the Z, they were predicted. That's a very good question. Yeah. The quarks, no predictions. The let me be very rough about it. Basically, no predictions here. The W mass was predicted precisely in advance of its discovery. And the Z boson mass was discovered, and the Z boson mass was predicted precisely in advance of its discovery. And that aided the discovery. And in fact, it aided it so much that if you look at the original data sets which found the W boson, okay, they knew the mass. And those data sets, which they used to claim the existence, were no longer past the cuts or the consistency requirements for the later data analysis. In other words, they claimed the discovery because they knew it was there based on crappy data. And then they didn't even include that data in the later data analysis because they were so sure they had seen it, and they did. So it helps to know in advance what you're looking for. And they certainly knew about the mass of the W and the Z before they were found. And Rubia and Vander, somebody or other, won the Nobel Prize for finding that at CERN.
Is that hindering discovering the mass of the Higgs then?
No, because the problem with the mass of the Higgs is that we don't have a clear prediction of its mass value. We don't know in advance what its mass value is. We just have a little bit of inference from pre-existing data, whereas the W mass was predicted dead on. I mean, it was known it was going to be 80 GeV. And it was found at 80 GeV. And that was done by Steve Weinberg. And the Z mass was predicted 90 GeV. That really helped find it. And the Higgs is unconstrained. There's no advanced number. There's just a window. And the window is big. But the window, there's a bias in the window based on pre-existing data, but there's no predicted single number. And the top quark, people were shocked it weighed 170 GeV. I mean, before the top quark was discovered, no one imagined you could have a quark that weighed so much. The lightest other quark is the bottom quark. It weighs 5 GeV. And the top quark came in weighing twice the W and the Z. I mean, the top quark is just so far out there. Very few people imagined that the top quark could weigh 170 GeV. It's really high. Yeah?
Can you explain more about, sorry, I don't understand
Yeah.
much of this, so maybe not be a great question, but the W and the Z and the Higgs, I mean, they're not in this pretty little matrix. You said they were force particles, or what exactly are those, and are there others, and how does that all relate?
Okay, that's a big question. The question is, what are the WZ and all the other force carriers? That's a big question, but let me just say the following thing. In the electromagnetic theory, in electromagnetism, it's basically a theory of electrons and muons interacting electromagnetically, and there's a force carrier particle called the photon. And the photon is a massless spin 1 particle, which is seen all the time. Photons are hitting your eyes, and it's associated, though, in this theory with a force. In other words, there's kind of always this in quantum field theory or in elementary particle physics. Forces are associated with particles. The exchange of particles gives rise to forces. And in a sense, it's the exchange of photons that gives rise to Coulomb forces. So in the electromagnetic theory, there's charged particles and the photon. Well, there are other interactions in nature. For example, there's a thing called beta decay. If you put a neutron on the table and you wait a few minutes, it will spontaneously decay into a proton and 2 neutrinos. Okay? No, a proton, an anti-electron, and a neutrino. I misspoke. I have to conserve charge. A neutron goes to a proton, an anti-electron, and a neutrino. No, I got that wrong. Neutron goes to proton, electron, and a neutrino, and an anti-neutrino. I don't know. I can't get it straight. But a neutron decays into some things. Okay? Now that reaction is mediated by a force called the weak force. And the force carriers of the weak force are the W, plus, minus, and Z. And they are an integral part of the theory of the weak interactions. Now, you're probably, weak interactions are very, very important in processes in the sun and in certain kinds of reactions, but they have less impact on your everyday life, which is probably why you don't know that much about them. Even though they're a fundamental force and they have a lot of wonderful properties, they don't impact your day-to-day life as much as, let's say, the electromagnetic force. But these particles are an integral part of what's called the standard electro-weak theory. This model was written down by Weinberg, and it augmented in a way by Glasgow and Salam and others. And it gives you a consistent way in which particles can undergo beta decay, in which the Z boson can decay into neutrinos, and all kinds of reactions which are important for burning in the sun, etc. And one of the ingredients of this is the Higgs boson. And the Higgs boson is a particle which is integral to this discussion, but whose mass is not predicted by the theory and is the one we're waiting to see. I don't know how much more specific I can be. The other force carriers, which I did not mention, are the force carriers of the strong interactions. Those are called gluons. And there are 8 gluons, and the reason they're called gluons is they glue the proton together, they keep the quarks together. And the theory of the strong interactions, which is really the theory of what holds the proton together, what holds nuclei together, is called sometimes quantum chromodynamics, and that has been very successfully tested, but with much less precision than the theory of the weak interaction. And that's basically because it's much harder to do precise calculations in the theory of the strong interactions than the weak interactions. Basically because we do a perturbative expansion, and the perturbation theory is in a very large coupling constant, and in quantum electrodynamics and the weak interaction, we do perturbation theory in a small parameter. We have much better control. So those are the other, I didn't mention those, so, but we would complete this list entirely if I include the photon, which I read as a gamma, and the 8 gluons. And now, if I include the 8 gluons, the photon, the Higgs, the W plus minus and the Z, and the 12 fermions, that's the entire Standard Model. There are no other particles in nature. Oh, graviton. Yeah, I'm not talking about gravity.
So what is dark matter made of?
I don't know what dark matter is made of. Those are great, great mystery. You know, I don't know what dark matter is made of. There are, you know, that's a very, very good question. I mean, I just was talking about the LHC. What the query is about is dark matter. Now, I think most of you know that if you look out with a telescope and you look out in the sky and you look at objects very, very far away, you see only objects, you basically only see objects that are luminous. That's what you see with a telescope, objects that are emitting. And dark matter is matter out there which is not emitting. It's not glowing. You don't see it with a telescope. But you can infer its existence. And the reason you can infer its existence is because, for example, if you look at a galaxy, and you look at a galaxy and it's spinning around its center, and the way you can measure that spin is looking at the Doppler shifts of the stars in the galaxy. And you'll see that some part of the galaxy is coming towards you, and some part is coming away from you. And you can then look at it head edge on, and you can look at the velocity versus the distance from the center. And you can use that simply using Newtonian mechanics, just Newtonian mechanics. And if I give you the velocity versus distance relation for an orbiting object, you can infer the mass inside the region that the outer things see, from the outer particles. For any given radius, you can figure out how much mass is inside to give that orbit, those orbital characteristics. And from that, you infer that galaxies have 10 times more mass than they are luminous. And there are many other reasons to suggest that the universe is filled with dark matter, at least 10 times or more the amount of ordinary matter. There are also reasons to suspect that this matter is not made of ordinary protons and neutrons. And the reason has to do with Big Bang nucleosynthesis. You know, we have a very good fossil record for what the universe looked like shortly after the Big Bang. I haven't made any connections to the Big Bang here. I haven't had time. But we have a very good fossil record for what the universe looked like right after the Big Bang. And that fossil record is the abundance of elements around us, the composition of stars, the composition of the interstellar medium. And all of that can be very, very well understood by understanding simple particle physics processes when the universe was hot and small. And if you look at those processes, you can infer the amount of baryonic or ordinary matter, and the amount of matter which you get from that is sort of consistent with what we observe today for luminous matter, which suggests, therefore, that the dark matter is not ordinary. So when this guy says to me, what do I think, dark matter is, I don't know. I mean, it could be the most happiest thing it could be, the best thing to be, is if dark matter is a form of elementary particle, which is not like a proton or a neutron, I use the word baryonic. That means that it undergoes the strong interactions. But a form of dark matter, that dark matter is a non-baryonic form of matter, which is somehow made at the LHC. If the LHC produces a new type of particle, which can then be identified as the dark matter, that'll be huge, because it'll make a wonderful connection between cosmology and particle physics. And we would be very, very turned on by that. But I have my own little pet theories for what technicolored technobaryons. I have my own pet theories, but I don't have anything I would really bet big money on. Yes?
Since that more the masses of fundamental inputs, can it be theorized that dark matter could be matter which forms a standard model but with different input values, different masses?
Oh, the question is, is it possible that dark matter is just a particle like this, but something which has a different mass or something? Well, one thing is it can't be light, because if it's, for example, if it's like those particles, let's say it's charged. Well, there have been so many particle accelerator experiments to date in which you've collided together things which, through the electromagnetic interaction, would make charged particles. There are no unknown charged particles which are being produced electromagnetically, assuming it's charged and it interacts in a normal way electromagnetically. I don't care what other property it has. If it weighed under 200 GeV, it would have already been made at LEP or some other accelerator. So it seems very, very hard to imagine that there are particles which look like these, which are light, because we would have made them in accelerator experiments. They would have been produced. So that seems unlikely. Whether, could dark matter be a very heavy, non-decaying lepton? Maybe. Could it be some super heavy electron? But then you'd have to tell me why it's not decaying. Because you see, the tau decays to the mu, and the mu decays to the electron. So when you say if it was like these guys, then they typically decay down. So you'd have to stabilize it in some way. So dark matter is a pretty tricky business because it has to be a form of matter which is not like ordinary quarks. It has to be stable, and it has to have avoided detection to date. So it's a very great mystery. I mean, that's a huge and wonderful mystery. And if the LHC finds dark matter, that'll be the best thing imaginable. But of course, you'd have to prove it's the same thing as what's out there. And there are direct dark matter detection experiments on Earth, but obviously they haven't found dark matter, or I would have told you about it.
How can you detect dark matter when it's not observable except by experience?
Well, because they have very, very weak scattering. That's right. Good question. Well, sometimes people stipulate that the dark matter could have a very, very weak additional forces. And then when you make a dark matter model, you have to contrive it so that it just is on the edge of being seen by the existing experiments, but has avoided detection to date. Usually that's not the easiest thing to do. Yeah, a lot of questions. Go ahead.
So getting back to your explanation of the neutrinos being left-handed.
Yeah.
So what happens if you're looking at them in a reference frame that's moving so fast?
Right. They become right-handed. That's absolutely right. Well, you see, you're absolutely right about that. The neutrinos, being left-handed, if a particle is massless, see, we used to think the neutrinos were massless. We now know they're not. If a particle is massless, then it can never be seen at rest. So it has no rest frame. So as long as it has no rest frame, it's shooting along at a very high velocity, and then you can measure its angular momentum and see it points opposite to the direction of momentum. But you're absolutely right. If a particle has a non-zero mass and it looks left-handed in let's say the lab frame, if you get into a frame in which it's going the other way, it will flip to be right-handed.
So then what does it mean when you look at the interaction?
Well, we take care of that. I mean, I can't really explain that, but yeah. But an example of that is the electron. For example, for example, if a pion, which is a particle, decays into, oh no, that's not good. A pi plus. A pi plus decays into, let's say, an E plus and a neutrino. This is a particle that decays into this. These guys come out back to back. So the neutrino is left-handed, and this electron, oh man, I'm not saying this too well. This electron, it's sort of a bad example. It wants to be left-handed, but it can't because of conservation of energy, conservation of angular momentum. I can't do justice to this. It's okay. I can't do justice to this fast enough. I mean, I have it under control. I really do. It's just not obvious. It's really okay. We can deal with particles having mass and still have parity violation. And if you get in the frame in which they're going the other way, they flip their handedness, and it's all okay. It's all okay. I just can't deal with it now. But you have too many questions. Someone else. Yeah.
Are there any other particles that are predicted by like the theory of
By the what?
By like any of the other, like string theory.
Oh, well, oh, sure. Once we open up the floodgates of alternative models, then the list gets endless, right? If I, for example, if I say the most common thing, one of the things that people love to talk about is supersymmetry. Now, supersymmetry is a symmetry which exists in almost every string theory. And string theory is very, very popular. So a lot of people think that supersymmetry should be found in nature. Okay? Now, supersymmetry is a symmetry which tells you that you can have that for every fermionic state, a fermion, there's a boson with the same mass. And for every boson state, there's a fermion with the same mass. So if the world was supersymmetric, then the electron would have a bosonic, meaning a spin zero, friend called, I think, the selectron, with the same mass. And the muon would have a bosonic friend, the smuon or something, with the same mass. And everybody else would have, the Higgs would have a Higgsino, which would be fermionic. And there would be all these particles, right? And there are certain mathematical reasons why that might be a very nice thing to have. The trouble is, it ain't so, right? There is no bosonic partner of the electron. There's no charged spin zero particle that weighs 500,000 electron volts. We would have seen that. That would not have been able to avoid detection. So all of the supersymmetric partners of these particles have to be somehow or another, you have to explain why their masses are not the masses of their partners, and why their masses are so high that we would not have yet seen those particles. And in order to do that, you have to break supersymmetry. So you have to impose a symmetry, and then you have to violate it. And the violation has to be strong enough to shoot the masses of those particles up. So, but in a supersymmetric version of the standard model, every particle here has a counterpart. The fermions have bosonic counterparts. The bosons have fermionic counterparts. And there's a plethora of new particles. And there are a huge number of new parameters which you can use to help fit the data. So the supersymmetry is very popular as a thing to look for. One of the reasons is because it is consistent. String theory predicts it. The other thing is it's very definite. The other thing is it has enough parameters that you can make it agree with the predictions of the standard model. And also there are some supersymmetric candidates for dark matter. And that's a nice thing, because if you have a supersymmetric dark matter candidate, well, you know, maybe you kill two birds with one stone. Or well, you kill one bird with one stone. I guess you get the dark matter, and then you get to find the supersymmetric particle at the LHC. So that would be great. I mean, if they found a supersymmetric particle at the LHC, which was the dark matter, that would be very compelling. But there's a lot of baggage that comes with that extension of the standard model, like another particle for every particle which has not yet been observed, which I think is a lot. Go ahead.
Earlier you mentioned the fossil record.
The what?
Fossil?
The fossil record. I meant the Big Bang, yeah.
And you mentioned there's this distribution of particles that come from that.
Yes.
Do any of those extend like in a histogram or a distribution that beyond which we've seen, which includes the dark matter? Is there any correspondence between the two? What we might not be.
You know, is there evidence, let's say, in like cosmic microwave background radiation or something like that for dark matter? I believe, I may be speaking out of turn, but I believe the following. You know, there is this cosmic microwave background radiation, and it's anisotropic. Originally, people thought you had to be the same everywhere in the sky, but it's turned out that it has variation in the sky, and that variation can be accounted for by the inflationary model of the universe and by certain assumptions in elementary particle physics. And I believe that there's a thing now called the vanilla model, which vanilla means just the plainest model, in which you assume a certain amount of non-baryonic dark matter, a certain amount of dark energy. We haven't talked about dark energy at all. And I believe that it's all consistent with there being, even the cosmic microwave background radiation data is consistent with there being a non-baryonic dark matter component to the matter density of the universe. So that hangs together. I've been not going into that because I wanted to talk about the LHC, you know. Yeah?
Do these particles all exist in nature outside of particle accelerators, or do they decay so fast that, like, the second and third generation ones don't exist?
You are made of up and down quarks and of electrons, and you know you don't see too many neutrinos are going right through you right now, right? Because neutrinos are emitted from the sun and from supernova, and right now there are, I forget how many billions of neutrinos going through you. So there are certainly neutrinos going through you routinely, and it's all three types of neutrinos that go through you. So you're being constantly bombarded by 3 generations of neutrinos. So those certainly pass through the Earth all the time. But these charged particles, when they are made, they decay rapidly. So these can only be seen in the following environments: in an accelerator, in the early universe, or in a cosmic ray event. You know, there are cosmic rays, which are extremely energetic particles which hit the upper atmosphere. And so the origin of those cosmic rays is not totally understood. But when those cosmic rays hit the upper atmosphere, they create showers of particles. And they create these guys who then rapidly decay. So these particles are not, they're not, again though, I want to emphasize, they are not building blocks to the world around you. But from a particle physics standpoint, they are all equally fundamental. Because again, you only make things out of stable particles. And the fact that it's stable makes you make it. But from my point of view, these are equally interesting. I don't care that I'm made of up quarks. The charm is as interesting to me. Yeah?
So there are 8 gluons, 1 photon,
Right.
like WZ and Higgs for the other 4.
Right.
Why are they not, why are there 8? Why is there only 1?
I don't know. I don't know. Why? You see, those why questions, I don't have answers to. Why are there 8 gluons? Why is there a W plus minus and Z? Why is there a Higgs? Why are there 3 generations? Why do these particles have the masses? Those big why questions we don't know the answer to. That's why particle physics is still reaching. See, again, maybe I should end soon, but the real frustration in particle physics, which is that there are these big why questions. Like why 3 generations? Why 8 gluons? Why this variety of particles? Why is the mixing angles what they are? Why are, you know, you could ask maybe why is parity violated, although I would ask why shouldn't it be violated? But, okay, fine. So there are all these why questions. But then when you take the detailed model, you turn the crank and you make predictions, everything's perfect. So that puts you in a very tough spot. It would be easier if you had contradictions. Puts us in a tough spot.
But I mean, you said with the 3 of these, the 4th generation, there's reasons to believe they're on the 4th generation.
But that's experimental. That's not really theoretical. I don't have a profound reason for that. I just have experimental evidence that there is in the 4th generation. But if you said to me, forget the data, could you mathematically add to the standard model another generation, I would have no problem. I would just write it down. You can name them whatever you want. I'll name them after people in the room. I'll just put them in there, and they'll be part of the standard model. I could do that. In other words, what would be interesting is if you said to me, no, if you put that into the theory, you're going to get a mathematical contradiction. You're going to, you know, your theory is going to predict 2 equals 7. Or you're going to predict, you know, the probability of something happening is bigger than 1. Or something like that. Then you say, well, okay, I can't have it. But no, I have no problem accommodating another generation. I would have no problem changing the masses of these particles. Well, I mean, if I eliminated the W and Z, I'd be eliminating a force of nature. I mean, that's, you know, that would be probably.
If there was more than W and Z, you would eliminate the force of nature?
No, I thought you said, no, if I eliminated the W and Z, I'd be eliminating the weak interaction.
Not eliminating them, I mean adding more. Like, why not, if there were a 9th gluon, is it
well, yeah, the 9th gluon probably is not consistent with experiment. I mean, there are some structures which we do have, but the structures are not as constraining as we would like. Yeah, there would be hard to have 9 gluons. But those are for kind of technical reasons.
Question?
Sure.
most of these particle reactions seem to emit neutrinos, but
Yeah.
they never take neutrinos in.
No.
So how much mass has been generated, lost to neutrinos through this process?
Oh, huge. In other words, when a neutron star explodes, I think half of its energy goes out in neutrinos. And it's, yeah, when a neutron, I forget the number because I'm not an astrophysicist, but I think when a neutron star explodes, half the energy comes out in neutrinos. And neutrinos do sometimes come in. For example, after supernova 1987A, there was a supernova explosion. A huge amount of energy came out from that in neutrinos. And those neutrinos passed through an underground detector and were picked up. So neutrinos sometimes do interact. We do see them. We saw the neutrinos emitted from a supernova. So neutrinos carry huge amounts of energy in astrophysical environments.
And is that mass enough to account for the dark matter?
No. No, neutrinos don't account for the dark matter. No. Oh, I meant the energy carried out. It wasn't the mass. No, when a supernova explodes, it's the neutrinos only have a little bit of mass. When a supernova explodes, the energy that comes out is the kinetic energy of the neutrinos. Yeah.
Maybe it's too experimental on
Yeah.
end, but I was going to ask what sort of things can be used to actually make detectors for these things? Are they observable directly or only inferable by?
Oh, he's asking about the detection. I don't really know. I mean, if you look at the LHC, there's these massive, strings of wires and silicon detectors and bubble and chambers, and I don't know. I'm out of my depth there. I don't really know how those things work. I just sort of have a gee whiz attitude. I I have no more idea how the LHC works than I know how my cell phone works. Yeah. Well, should we stop?
Yeah, you must be exhausted.
Well, it's okay. That's not the problem. Why don't I take one more question or two? I think you probably want me to shut up soon. Go ahead.
Quarks appear in quark-antiquark pairs and in three-quark triplets.
Yes.
But how come you don't get like two quarks and two antiquarks?
Well, that's a good question. Yeah, that's called the question of confinement, and that I think there.
That's for a single quark. I'm wondering,
Oh, why don't you get past? Well, he's asking, there is kind of an understanding of that from the strong interactions. He's saying that, if you find objects like the proton, they have 3 quarks. And if you find an object like the pi plus, it's made of a quark and an anti-quark. And we seem to only get those combinations, but that seems to be consistent with the theory. I would say the theory of the strong interactions kind of explains that. I can't explain that now, but I can assure you that the theory of the strong interactions explains it. So that is probably understood. I would say that's understood by the theory of the strong interactions. We do have a theory of the strong interactions, and it takes care of that. Okay? Okay, well, thank you. Thank you.